In the field of wireless communication, we know the channel sources and the frequency are limited. With this disability, it is quite impossible to provide service to a large number of subscribers. To prevent this problem, the concept or the technique of frequency reuse is introduced. In each cluster, a specific range of frequency is repeated so that the total capacity of the system can be increased without increasing its allocated bandwidth. Though the technique requires sufficient isolation among the signals for using the same set of frequencies so that the mutual interference among them can be controlled. The signal broadcast from the transmitter antenna gets attenuated with increasing distance. After a certain distance, the signal strength falls below the noise threshold level, and it is no longer identifiable. In this region, if the signal attenuates below the noise floor, the same radio resource can be used by another transmitter to send different information. In the case of cellular systems, the same radio source can be used by two basic stations with a sufficient interval apart. As a result, the same frequency gets reused in a layer of geographic area by two or more different base station users concurrently. Now, it is very important to select the set of base stations which will utilize the same set of co-channel cells. This cellular concept is the major solution to the problem of spectral congestion and user capacity. In a large geographical coverage region, cellular radio relies on an intelligent allocation and channel reuse. Cellular frequency reuse. Every cellular base station is allotted a group of radio channels to be utilized within a small geographic area known as a cell. Base stations of the adjacent cells are assigned channel groups which hold different channels than neighboring cells. Base station antennas are outlined to achieve the wanted coverage within a particular cell. By restricting the coverage area inside the boundaries of a cell, the same group of channels are used to cover different cells that are separated by geographic distances fairly large to keep interference levels within sustainable limits. This designing method of selecting and allocating channel groups for all cellular base stations within a system is known as cellular frequency reuse or frequency planning. Cell cluster. Let us consider a cellular system that has a total number of S-duplex radio channels. When each cell is allocated with a group of K channels, that is, K is less than S, and the S channels are distributed among N cells into individual and disjoint channel groups of the same number of channels, then S is equal to Kn. The N cells that collectively uses a complete set of frequencies is known as a cluster. Now, when a cluster is replicated m times within the system, the channel capacity C becomes C is equal to Mkn, which is again equal to Ms. Co-channel cells. A giant cluster size causes decrease the radio among the cell radius and the distance between co-channel cells and reduce interference. The value of n is a function that shows how much interference can occur through a mobile or base station that can tolerate while preserving a sufficient quality of communications. To connect without gaps within adjacent cells, the geometry of hexagons is such that the number of cells per cluster n can only have utilities that satisfy n is equal to I square plus ij plus j square, where I and j are non-negative integers. With this, we have come to an end of this session, and today we have learned Introduction and Need of Frequency Reuse, Theory of Frequency Reuse and its Technique, Cellular Frequency Reuse, Cell Cluster Equations and Parameters, Co-channel Cells Equation and Parameters. We will meet again with another topic of wireless communication. Bye.